morning, and aloha.
Good job!
We are Team AeroSpace Meridian from Makua, Lani Christian Academy in Kailua Kona, Hawaii. My name is Maya Kalilau, and these are our team members: Rachel Lorenzo, Hannah Husek, Lena Wolcott, Jade Whiting, Austin Pham, our team leader, Josiah DeLuz, Logan Russell, Nolan Prius, Josiah Richards, and Christian Williams. We present to you our space ring, the ASM Corpus. There are 4 phases of our project. First, we propose the Shackleton Crater Base to supply the engineers of the ASM Corpus with food, water, and fuel during the construction of the Corpus. Second, the asteroid Ryugu is mined for raw materials for building the ASM Corpus. Miners and engineers essentially transform the asteroid into the ASM Corpus. Third, the ASM Corpus is constructed as a space ring. Its design features radiation and high-velocity particle shielding based upon the data we have collected from our own experiments. And fourth, once the ASM Corpus is constructed, it will be transferred into a circular orbit in the vicinity of Mars. This placement will allow the Corpus to be an outpost for Mars exploration, a rest stop for asteroid belt miners, and a permanent space colony for the mass diversity of cultures and minds willing to unite together amongst the stars.
The first phase of the ASM Corpus is the development of the Shackleton Crater Base on the Moon. The lunar base is very essential because it will provide food for the engineers constructing the ASM Corpus at Ryugu and fuel for orbital transfer. But how can we grow food on the Moon? Well, we're planning to use Lunar Regolith as our growing medium. However, Lunar Regolith can cause severe complications. These razor-sharp microscopic particles can come in contact with the skin, eyes, or be inhaled into the lungs, causing severe cuts and inflammation. Regolith is so sharp that it can cut through Kevlar and spacesuits. However, based on the research that we've conducted, it is determined that lunar regolith can be converted into arable soil. To conduct our experiment, we used samples of regolith simulant from Hawaiian soil. This chart compares the mineral composition of lunar highland and lunar mare regolith with Hawaiian regolith simulant from 2 island locations. Lunar regolith and Hawaiian regolith simulant share almost the same composition across 10 significant minerals. This is a block of sintered regolith simulant. Sintered means that it was heated to form a solid block. We then scraped grains from the sintered regolith for examination. Here, Hannah, Lena, and Maya are recording the size of the grains. In this image, the blobs that you see are the grains of regolith simulant against a 1 millimeter scale. As you can see, the grains are less than 1 millimeter in diameter, varying in size from 100 to 500 microns. In this image, we see a comparison of unsintered and sintered regolith simulant. To your left, the unsintered regolith simulant is fine and powdery. The largest grains are less than 100 microns, and many grains are less than 10 microns. To your right, the sintered regolith simulant is several hundred microns in size. In conclusion, lunar regolith that has been sintered and attritted is safe. It is no longer the sharp, fine dust that can harm people's skin and lungs. We can confirm that lunar regolith, once sintered and attritted, can be used for farming on the Shackleton Crater Base. The Shackleton Crater Base is also essential to the production of rocket fuel. We are planning to access water hidden in the craters of the Moon's south pole. Our team member, Nolan Priest, put together the electrolysis device that you see here. The current generator sends electricity through the water samples. The water is then split into oxygen and hydrogen, which are captured in the different containers. We conducted the experiment to test on 3 water samples: distilled water, tap water, and lunar water that is contaminated with basalt soil. We conducted twice, once with constant power and once with constant voltage. In this image, Austin is recording how long it took to produce hydrogen gas. Here are our results. The height of the bars represents how many seconds are required to produce hydrogen. In both experiments, we've discovered that lunar water contaminated with basalt soil achieved a higher rate of electrolysis than distilled water. To conclude, lunar water can be processed into rocket fuel without being purified. This means that we can save time and energy.
The construction of a space ring will require a large amount of resources. Therefore, the ASM Corpus will be constructed out of the asteroid Ryugu. Our construction rockets will assume a stationary orbit 400 meters above the best surface mining location. Then, automated robots will be lowered from tethers composed of braided dynema, where they'll begin extracting resources required for the construction of the Corpus. Shielding is probably the most important part of any space colony, since it protects the inhabitants of the Corpus from high-velocity particles, otherwise known as HVPs, and the solar radiation. We have designed a multi-layer shielding for the Corpus. To test how different shielding designs protected against the HVPs, we used a high-powered rifle in order to observe how different shielding designs reduced bullet penetration. In this photo, you can see the ASM team preparing the capture units required for our ballistics test. Through experimentation, we have found that a diamond-shaped shielding structure is an effective way to stop HVPs. The diamond shape allows for the kinetic energy of the HVPs to be diverted into multiple areas. Therefore, our first layer will be composed of a 1 centimeter thick layer of corrugated and angled Ryugu alloy. Our second layer will be 3 centimeters of substrate from the asteroid Ryugu, which will be used to absorb the kinetic energy of any penetrating high-velocity particle. In our field test, we also tested Dyneema, a Kevlar-like material. Dyneema proved to be the most protective of all, reducing bullet penetration more than any other metal configuration. Therefore, for our third layer, we will be using a 6 millimeter layer of Dyneema in order to catch any remaining high-velocity particle. Water and substrate are readily available on the asteroid Ryugu. In this picture, you can see water on the right and substrate on the left. The darker areas represent penetration by radiation, while the lighter areas represent resistance to the radiation. As you can see here, water is an effective blocker of radiation. However, with increased depth, substrate proved to be even more effective. Therefore, for our fourth and final layer, we plan on using a 10 centimeter layer of substrate in order to block the radiation. Docking poses a special challenge for the Corpus, since it spins in order to generate artificial gravity. We chose a less radical method of docking. Instead of spinning the entire central hub of the Corpus, we plan on spinning only the spacecraft itself, so that relative to the spacecraft, the Corpus will appear still. Then, docking arms from the Corpus will approach the spacecraft and lock onto it, allowing for the transfer of both cargo and people.
Producing electricity is a unique challenge for the ASM Corpus. It can't use fusion reactors because the technology is not ready. Oil and other fossil fuels are not viable since they must be supplied from the Earth. Solar panels are the best option. To save money and materials, a single solar array will be placed on the side of the ASM Corpus that faces the sun. In this image here from JPL shows the asteroid Ryugu as the white ellipse. As you can see, Ryugu has a near-Earth perigee and a near-Mars apogee. Because the ASM Corpus will be constructed from the asteroid Ryugu, it will have the same elliptical orbit. Once fully constructed, we'll begin an orbital transfer. Now, an orbital transfer is dependent on a delta V of 2.5 kilometers per second. This requires an enormous amount of fuel. On December 2033, we will receive a fuel supply from the Shackleton crater base, while in near-Earth vicinity. Then, in May 2037, we'll prepare for an orbital transfer. We'll blast the ASM Corpus from the elliptical orbit of Ryugu into a near-Mars orbit, right outside Mars' gravitational sphere of influence. Once the orbital transfer is complete, the ASM Corpus will begin to spin, creating an artificial Earth-like gravity. Now, there are several reasons why we decided to move the ASM Corpus near Mars. Number one, the 615-day year makes attitude control simple, requiring a 0.6 degree adjustment per day to keep the solar panels facing the sun. Number two, placing the Corpus near Mars allows Martian exploration. And number three, the ASM Corpus becomes an easy relay point to other asteroids that can be developed. Now, the ASM Corpus project is not only a space ring, but a call to excel in our knowledge as students and professionals as we look further into the beauty of space. Thank you, ladies and gentlemen, for listening to our presentation on the ASM Corpus. And a big thank you to our teacher and mentor, Frederick Herman. Also, thank you to Ms. Lynn Zielinski, who has helped us to improve this presentation. And a big thank you to Al Globus, who has dedicated his time and effort in creating the NSS Space Settlement Contest, giving students like us a chance to share in our knowledge, creativity, and imagination as we look further into space exploration. Thank you, mahalo, and aloha.
Oh my gosh, I hope you're as impressed as I am.